Welcome to the second session of our course, Introduction to Gurobi and Setup. In our previous session, we explored the theoretical why behind optimization. Today, we move into the practical how. This session is presented by the Institute of Computer Science at Forth, in collaboration with the TwinODIS project. We are going to prepare our systems and our minds to transition from abstract mathematical models into working executable code. Our roadmap for this session is divided into 4 main segments. We will begin with Section 0, an Introduction to the Decision Intelligence System, or DIS. This provides the broader business context for why we optimize. Following that, we will move into Section 1, getting started with Gurobi. This is where we will walk through the specific steps for installing the Gurobi engine on your local machines, whether you are running Windows or Linux. In the second half of the session, we will dive into Section 2, the Gurobi Python API. This is the most popular way to interface with Gurobi, and we will cover the key features that make it so powerful. In Section 3, we will look at how optimization actually works inside Gurobi, focusing on environments, parameters, and attributes. Finally, we will conclude with a hands-on exercise in Section 4. We will build and solve a practical power generation cost minimization model, seeing the entire pipeline from data to decision. Let's start with a fundamental question. What is the difference between a good decision and an optimal one? Every day, managers and engineers make decisions that are good, based on their experience, intuition, and a general understanding of the problem. But in a modern business environment, even good decisions can cost millions of dollars in lost revenue, wasted time, and inefficiently used resources. Why is that? Because there is a vast difference between a decision that works and a decision that is mathematically best. Our human brain simply cannot process every single possible path and every tiny detail at the same time. DI's technology allows us to identify the absolute best action based on your specific goals and your hard constraints. It enables businesses to make fast, confident, and unbiased decisions, even in the middle of rapid global change or disruption. So how does a decision intelligence system actually function? It starts with you, the modeler. You input the precise details about your complex real-life business problem, your goals, your costs, and your limitations. Once the data is in, the DIS gets to work, exploring the trillions of different ways you could achieve those goals while strictly respecting your constraints. This is more than just finding an answer. It is a tool for strategic exploration. If the business situation changes, or if you want to explore what-if scenarios, you don't need to rebuild the entire system. You simply adjust your inputs and run it again. This allows for a dynamic, responsive way of managing resources that evolves as quickly as the real world does. To understand how to build a model, we must first understand the decision intelligence pipeline. Think of a DIS as a sophisticated engine that requires 3 specific types of fuel to run. First, your business objectives, which define exactly what success looks like for you. Second, your business constraints. These are the hard boundaries and limitations you face, such as budget, labor, or physical space. Third, your decision variables. These represent the specific questions you are asking the system to answer, like how many units should I move or which route should I take. Once these inputs are defined, the DIS processes them to produce a clear, actionable output. This output isn't just a suggestion. It is a detailed set of decisions that are mathematically proven to optimize your objectives while strictly respecting every single one of your constraints. Where do we see this in action? The impact of DIS is global and spans across industries. In transportation, giants like Air France, Swissport, and Uber use these systems to create optimal routing, staffing, and maintenance plans. Every minute an airplane sits idle or a driver takes a suboptimal route is a cost, and DIS minimizes that waste. In professional sports, the NFL and the BK Basketball Bundesliga use decision intelligence to plan their massive game schedules, balancing travel distances, TV, broadcasting slots, and stadium availability. Even in manufacturing, companies use these tools to manage the entire life cycle of a product, from the procurement of raw materials to production on the factory floor and final distribution to the customer. In each case, the system is handling a level of complexity that would be impossible for a human team to manage manually. If optimization is so powerful, why isn't it easy? It's because the questions we ask are inherently difficult. We aren't just asking how do we make money. We are asking complex, multi-layered questions like which specific discounts should we offer to which specific customers to maximize total revenue? Or what is the absolute least costly way to reroute shipments during a global disruption? The difficulty comes from conflicting goals. You are often trying to maximize production while simultaneously minimizing environmental impact, or maximizing returns while minimizing risk. When you add in complex interdependencies such as fluctuating energy costs, regulatory constraints, and sudden global disruptions, the number of moving parts becomes staggering. TwinODIS is the tool that navigates this mathematical storm to find the one path that satisfies all these competing forces. It is common to confuse machine learning with decision intelligence, but they serve two very different yet complementary roles. Machine learning is predictive. It uses historical data to tell you what is likely to happen. For example, ML can predict a customer's likelihood to buy or the probability of a machine failure. Decision intelligence, however, is prescriptive. It tells you what you should do about those predictions. Think of it this way. ML predicts there will be a supply chain issue. TwinODIS then identifies the least costly way to reroute your shipments to solve it. ML predicts that a price will move, and TwinODIS calculates exactly how to allocate your capital to take advantage of that movement. ML provides the foresight, but TwinODIS provides the action. Now let's get Gurobi running on your system. For Windows users, the process is straightforward. Visit the Gurobi download page, download the MSI installer file, and launch it. By default, Gurobi will install to your C drive in a folder named Gurobi 1202. You can choose a different directory if needed, and you can always rerun this installer to repair or uninstall the software later. For Linux users, you will work primarily in the terminal. First, use the tar command to extract the downloaded package. Next, you must set your environment variables in your bashrc file. You will define Gurobi home, and then add the Gurobi bin folder to your system path, and the lib folder to your library path. Finally, run the command source /bashrc to apply the changes. Regardless of your platform, once these steps are finished, the Gurobi engine is installed and ready for a license. Now that Gurobi is installed, we need a way to talk to it. We will be using Python. If you are new to programming, you couldn't have picked a better starting point. Python is famous for being incredibly easy to learn with a clean, simple, and compact syntax that almost reads like English. But Python isn't just for beginners. It is the industry standard for professional developers, especially in the fields of data science and artificial intelligence. What makes Python a great choice for mathematical modeling is its massive open-source community. There are tons of ready-made libraries for scientific computing, and the language syntax itself looks very similar to standard mathematical notation. We will also be utilizing Jupyter Notebooks, which provide an interactive graphical environment that lets us see our code, our notes, and our results all in one place. To work effectively in this course, you need to understand the two main components of a Jupyter Notebook, the kernel and the cell. Think of the kernel as the brain of the notebook. It is the computational engine that lives in the background, waiting to run and process your code. Every notebook is linked to a specific kernel, in our case, a Python kernel. The cell is the building block of your work. It is a specific section where you can write either code or text. When you run a cell, the code is sent to the kernel for execution, and the results are displayed directly beneath it. This structure allows you to organize your model into small, testable parts, making it much easier to catch errors as you build. When you are working in a notebook, you will notice that everything lives inside these cells. When you add a new cell, it appears with a green border. This is an important visual cue. It tells you that the cell is active and ready for your input. As we progress, we will use two different types of cells. Code cells are for your Python commands and your Gurobi model instructions. Markdown cells, on the other hand, are for your documentation. They allow you to write formatted notes, add headings, or explain the logic behind your constraints using simple text syntax. This combination turns your code from a cryptic script into a professional readable report. On the right side, you can see a screenshot of Jupyter that consists of consecutive Python code blocks. Now we show different Markdown cells and their originating code before processing. Markdown is flexible and can provide different text sizes, headers, numbered or unordered lists. include hyperlinks, define structure, and many more. With our Python environment ready, we need to install the Gurobi library. This is the official Python interface for Gurobi. The most common way to do this is using the pip package manager. You will open your terminal or command prompt and type python pip install Gurobi. If you need a specific version to match a project, you can use the command python pip install Gurobi equals 12.0.2. Once the installation is finished, you can verify it by typing python pip list. This will show you all your installed packages, and you should see Gurobi in that list. One important note, while pip is the fastest way to get the library, it does not provide the Gurobi license tools. For those, you will still need the full Gurobi installation we performed in the previous steps. For those of you using the Anaconda or Mineconda distributions, you can install Gurobi directly through the Conda package manager. This is often the preferred method for data scientists because it handles complex dependencies automatically. In your terminal, you would use the command conda install c Gurobi. The -c flag tells Conda to look specifically in the official Gurobi channel. If you need the specific version for this course, use conda install c Gurobi equals 12.0.2. One important reminder, Gurobi is optimized for specific versions of Python. Before you install, ensure your environment is compatible. You can always check your current setup by typing conda list or conda list and followed by your environment name. This ensures all your tools are perfectly synchronized before we start modeling. In some professional or high-security environments, you might not have direct internet access on your computing machine. In these cases, you can perform an offline installation using a wheel file. The process involves 3 steps. First, download the appropriate wheel file for your specific platform from the PYPI website on a machine with internet. Second, copy that file over to your offline machine. Third, in your terminal, issue the command python pip install, find links followed by your directory path, and then Gurobi pi. Make sure you have right permissions for your Python directory, and if you are using a virtual environment, ensure it is active before running the command. This flexibility ensures that you can deploy Gurobi-powered solutions even in air-gapped or restricted network environments. It is worth summarizing the differences between these methods. The full Gurobi installer that we used earlier is the only one that includes the command line tools, the license activation utilities, and the C and C++ libraries. The pip and condo methods are lightweight. They are designed specifically for Python developers who want to get the Gurobi library into their environment quickly. However, remember that these lightweight methods do not include the Gurobi getkey utility needed to activate a new license. Typically, you will use the full installer once to set up your machine and license, and then use pip or conda to manage your Python library versions. To understand how Gurobi handles its settings, think about how we use global and virtual environments in Python, such as pip or conda. Just as you create a virtual environment to load specific packages without affecting your whole system, Gurobi uses environments as containers to isolate settings. The environment box represents your global setup where your master parameter settings live. However, when you create a specific model, it effectively acts like a working environment. It creates a local copy of those global settings just for that specific instance. This means you can experiment with different solver configurations in one model without changing the behavior of the rest of your system. It provides a clean, safe, and organized way to manage multiple optimization tasks simultaneously. For most of our work, Gurobi handles this in the background by providing a default environment, but understanding this global versus local structure is vital as your models become more complex. Now let's look at the 2 different ways we interact with a Gurobi model, through parameters and attributes. This distinction is key to controlling the solver's behavior. In the first box, we have parameters. These are the knobs and dials that control the operation of the Gurobi engine itself. You modify these before you start the optimization process. For instance, you might set a parameter to tell the solver how many threads to use, or which algorithm to prioritize. In the second box, we have model attributes. These are the inherent properties of the components inside your model. As you can see, attributes are divided into 2 categories: attributes of constraints and attributes of variables. For a variable, an attribute might be its lower bound or its current solution value. For a constraint, it might be its sense, such as less than or equal to, or its right-hand side value. In short, use parameters to tell the engine how to solve, and use attributes to query the state and data of the model. To finish our conceptual overview, let's look at attributes. While parameters control the how of the solver, attributes are used to query or modify the specific properties of the Gurobi model and its components. As you can see in the diagram, attributes are organized into 3 levels. First, we have model attributes, which describe the problem as a whole, such as the total number of variables, or the final objective function value. Second, we have variable attributes, which define the character of each decision variable, like its lower bound, its upper bound, or its name. Third, we have constraint attributes, which define the rules, such as the sense of the inequality or the value of the right-hand side. Think of attributes as the data points that make your model unique. You will use them constantly to extract your results after an optimization run, asking Gurobi questions like, what value did variable X take? Or how much slack is left in this specific constraint. We are now starting our Gurobi cheat sheet, a practical guide to the most common commands you will use in Python. We begin with model initialization. The model class is the main brain for creating and managing your optimization projects. Its primary job is to act as a container to which you will add your variables, constraints, and your objective function. In the code snippet below, you see how simple it is to start. After importing Gurobi as GP, you simply write model equals gp.model and give your model a name like my_model in quotes. This single line of code creates the workspace where all your optimization logic will live. Once the model is initialized, we need to create our decision variables. We do this using the commands addvar for a single variable or addvars to create arrays or matrices of variables all at once. When you define a variable, you can specify several key parameters. LB sets the lower bound, which defaults to 0, and UB sets the upper bound. The v-type, or variable type, is essential. As shown in our table, you can choose Gurobi.continuous for real numbers, Gurobi.binary for 0-1 choices, or Gurobi.integer for whole numbers. For example, if you want to create a 2-dimensional matrix of variables with a lower bound of -10, you would use the command z equals model.addvars 3 for lb equals -10 name equals z. This flexibility allows Gurobi to handle everything from simple production counts to complex multidimensional supply chain flows. The next step is defining our target using the setObjective command. This tells Gurobi exactly what you are trying to achieve. This command takes 2 arguments. First, the expression, which is a linear or quadratic formula of your variables. For complex models, we often use gp.quicksum, which is a high-performance version of the standard Python sum function. Second, the sense of the optimization. You must specify either grb.maximize for goals like profit or grb.minimize for goals like cost or waste. In the example on the slide, we are maximizing the sum of all costs C multiplied by variables X for every item in our list. This single line turns your collection of variables into a goal-oriented mathematical model. Finally, we define the rules of the game using addconstr and addconstrs. Gurobi supports all standard comparison operators, equals for exact equality, less than or equal to, and greater than or equal to. For a single rule, like x plus 2 times y is less than or equal to 10, you use addconstr and give it a name like capacity constraint. For multiple rules, like demand constraints across an entire set, you can use a generator expression inside addconstrs. You can even create range constraints by placing your expression between 2 values, such as 5 is less than or equal to 3 times x plus y, which is less than or equal to 20. This descriptive approach allows you to build very complex logical structures with just a few lines of clean, readable Python code. Once your variables, objective, and constraints are all defined, it is time to run the engine. We do this with the simple command model.optimize. But the work doesn't end there. After the solver finishes, we must check the model.status to understand what happened. As you can see in our status table, if the status is grb.optimal, congratulations, you have found the best possible solution. However, if it says grb.infeasible, it means your rules were contradictory. If it says grb.unbounded, it means you forgot to cap a variable. If the solution is optimal, you can then query the key post-solving attributes. You use model.obgvl to see the final score of your objective function, and you use the .x attribute on any variable, such as pst. y bracket teamwacket.x to see the specific value the solver chose for that variable. This is the moment your math turns into a concrete business decision. Sometimes you need to guide the solver's behavior using parameters. On this slide, we see the most common controls. The time limit parameter is vital for real-time systems. For example, setting it to 120 ensures the solver won't take more than 2 minutes to find an answer. The MIP gap allows you to stop the solver early if it finds a solution within, say, 1% of the theoretical optimum, which is often enough for large-scale industrial problems. You can also use the output flag to silence the solver's console log if you are running. It is part of a larger automated application. There are 2 ways to set these. You can use the model.setParam method or the preferred, more modern Pythonic way, model.params.timelimit equals 60. These controls ensure the solver works within your specific operational requirements. In order to use Gurobi in Python, we use the GorbaPy module. This contains all the necessary function and framework to formulate and solve our models. GPRead is a global function which returns an object of type model. The object model, which is the core of a programming implementation, contains several methods, like the optimize method, which is self-explanatory, and the printattr method, which output parameters of the model. Following that visual overview, let's look at the specific syntax required to manage these settings. First, we have parameters. You can set a global parameter for your entire script using gp.setParam, or as we prefer, set a local parameter for a specific model using model.setParam, or the direct model.params.timelimit syntax. This ensures your solver constraints are localized to the right problem. Next, we have attributes. You can modify them, such as giving a variable a human-readable name using variable.vrName equals total costs. Or you can query them after the solve, like checking variable.x to find the final value. We also see the use of the model.status attribute to confirm we actually reached optimality. Finally, remember to use model.disposed and gp.disposed default nev. This is the housekeeping of optimization. It frees up your memory and releases your license for other users as soon as your job is done. It is time to put all of this setup and theory into practice. We are going to build our very first optimization model from scratch. In this hands-on exercise, we will walk through the entire life cycle we've discussed today. We will start by defining our variables, then setting the objective function, followed by adding the constraints. Finally, we will run the optimize command and learn how to interpret those status codes and attribute values we just covered. By the end of this exercise, you will have gone from an empty Python script to a fully functioning, provably optimal decision intelligence tool. Let's open our Jupyter notebooks and begin. Let's now look at a typical formulation for and optimization problem using Gurobi. In this mathematical formulation, we start with an objective function, which is subject to either minimization or maximization depending on the nature of our problem. This is subject to some constraints which define the scope of the problem and range of possible solutions. In this setup, we have some data, known beforehand, like Cij in the right-hand side of the inequalities. All this boils down to determining the Xij variables, which represent the quantities of the elements we want. These can take a range of values, and the type is specific to the respective problem. Now it's time to translate the mathematical formulation to Gurobi code in order to translate it to Python code ready for solution. To start, we define the model using the gp.model command, which sets up a model object drawn from the Gurobi. If we have determined what the problem variables are going to be, we can define them in code using either addvar, which adds one variable at a time, or the plural of it, which facilitates batch addition to the model. Knowing the variables, we need to set the objective using the setObjective method. This determines the objective function, a minimizable or maximizable quantity of our choosing. Finally, similarly to the addition of variables, we can add our restrictions, the constraints, either one at a time or multiple at once. In any Gurobi project, step 1 is data definition. We start by importing our library and then we define our sets. We use the list I to represent our workers, labeled 1W2 and so on. We use the list J to represent our tasks, T1 through T3. The most important part of our data is the profit matrix, which we store in a Python dictionary called C. Each key in this dictionary is a pair or tuple of a worker and a task, and the value is the profit generated by that pairing. For example, the pair 1T1 might have a value of 10. This organized structure allows our model to isolate look up the worth of every possible decision the solver considers. Next, we define our goal using the objective function. Since we want to maximize the total profit of our assignments, we use the setObjective command with garobi.maximize. Look closely at the code. We use gp-quicksum to calculate the total profit. This function iterates through every worker I in our list I, and every task j in our list j, multiplying the profit value ci, j by our decision variable xi, j. This effectively tells Garobi, calculate the total value of all the assignments I choose, and make that sum as large as possible. Finally, we add the rules that make the problem realistic. Our primary constraint is that each task must be assigned to, at most, one worker. We can't have two people trying to do the same job at the same time. We use model.addConstries to apply this rule across all tasks in list j, the math says. For every task j, the sum of all workers I assign to it must be less than or equal to 1. Once this rule is in place, we reach the final step, model.optimize. When you run this line, Garobi's engine takes over. It analyzes the profit matrix, respects the one worker per task rule, and calculates the optimal assignment. In a fraction of a second. We have now moved from a business problem to data, from data to math, and finally from math to an optimal solution. The final step in our code is extracting and communicating the results. We don't just print blindly, we first check the status. We use an if statement to see if model.status equals grb.optimal. This ensures we are only looking at valid data. If optimal, we print the model.obgval to show our optimal total profit. Then we use a nested loop to look at every worker in I and every task in j. Because our variables represent yes or no decisions, we check if xi, j.x is greater than 0.5. If it is, it means the worker is assigned. This simple check allows us to translate a matrix of zeros and ones into a clear, human-readable report. Worker 1 is assigned to task 2. If no solution exists, our else block ensures the user is informed that the requirements were impossible to meet. Now let's apply everything we've learned to a new high-stakes scenario, power generation cost minimization. In this case, we are acting as a grid operator who needs to meet a city's demand of 500 megawatts. We have two power plants at our disposal. Plant A is our base load. Plant, it's cheaper at $20 per megawatt and has a maximum capacity of 400 megawatts. Plant B is our peaker plant. It's more expensive at $30 per megawatt, but it has an additional capacity of 300 megawatts. The question is, how do we split the production to keep the lights on for the lowest possible price? This is a fundamental problem in energy economics, solved thousands of times a day across the global power grid. To keep our data organized, let's look at this summary. Plant A costs $20 per megawatt and can handle 400 units. Plant B costs $30 and can handle 300 units. The total demand is 500. Even a quick glance shows a conflict. Our cheapest plant, Plant A, cannot meet the demand alone because its capacity is only 400. We know we must use Plant B, but the optimizer will tell us exactly how little of that expensive energy we can get away with using while still staying within our legal and physical limits. Before we code, we must formulate. We define our variables, XA and XB, representing the megawatts produced by each plant. Our objective is to minimize the cost, expressed as minimize Z equals 20 times XA plus 30 times XB. We then define our constraints. First, the demand constraint. XA plus XB must be greater than or equal to 500. Second, the capacity constraints. XA must be less than or equal to 400, and XB must be less than or equal to 300. Finally, our non-negativity rule ensures that XA and XB are both greater than or equal to 0. This 4-line mathematical model is the blueprint for our Python script. Now we translate that blueprint into the Garobi API. We start by importing model and GRB from Garobi API. We create our model object and name it power_generation. Next, we add our two variables. Notice we use model.addVar, giving them the names XA and XB, and setting their lower bounds to 0. Finally, we set the objective using model.setObjective. We type in the formula 20 times exa plus 30 times xb and specify grb.minimize. With just these few lines, the goal of our system is firmly established in the code. Next, we add the walls of our problem. We use model.addConstr 3 times, 1 for the demand of 500 and 2 for the individual plant capacities. By naming them demand kappa and cap B, we ensure our code remains professional and easy to debug. Once the constraints are added, we call the magic command model.optimize. After Gurobi finishes, we use a simple loop over model.getVars to print the name and the final value for each variable. This is where we see the transition from an empty variable to a calculated optimal decision. Let's look at our final results. Gurobi tells us that exa equals 400 and xb equals 100, with a total cost of $11,000. But why did it choose this? The interpretation is key. Plant A is cheaper, so the solver maxed it out at its full capacity of 400. However, that wasn't enough to meet the demand of 500, so the solver used Plant B to supplement the remaining 100 units. This is the merit order in action. The solver automatically prioritized the cheapest resource first and only used the expensive resource when absolutely necessary. This confirms that our model is working exactly as intended, providing the most cost-effective path to grid stability. As we wrap up Session 2, remember that this is just the beginning of what Gurobi can do. I have provided several links here to the official documentation. The attributes reference will be your best friend as you learn to extract more data from your models, and the Python API overview provides deep dives into more complex structures like multi-objective optimization and piecewise functions. Thank you for joining me for this setup and introduction. You are now ready to install Gurobi, set up your environment, and build your own decision intelligence models. See you in the next session.